Okay, I apologize for speaking in English, but it will go faster this way, and it will be less painful for you. So I want to talk about a subject that I've been working on for maybe too long. Some of you might remember that I talked about this at Collège de Lions some years ago, and it took a while to really get to a point where the ideas became rigorous, and that was in large part due to a collaboration with Eric Cancès. So the idea is to understand what the fundamental basis is for van der Waals interactions between molecules. And it's a complicated interaction, but I think we have a new way to understand it that, in fact, gives a rigorous solution to a multi-body Schrödinger problem involving two hydrogens. And so it's essentially an exact solution, something that has not been available for such a complicated problem. But first, since it's D-Day, and big things are happening. Yes. So it's the 70th anniversary, and here's a picture. My wife and I were fortunate to be out in Normandy a couple of weeks ago, and it's all dressed up for the occasion. Here's a typical store window in Bayeux. So that's what it looks like out there. But I know that everyone has a critical question on their mind. Why is Vladimir Putin in Normandy? We associate the Russians with the Eastern Front, not the Western Front, not with D-Day, not with Normandy. And I know many of you follow Garry Kasparov, the famous chess master, on Twitter, and saw this recent posting that he made. Putin has been invited to D-Day anniversary in France with Western leaders, he says. Did they want an expert in invasions? That was his question. And of course, that is true, that Putin is the most recent expert in invading another country. And so maybe that's why he was invited. But I don't think so. I think there's a better reason. And I just need to remind you about the famous squadron, we would say in English, the Escadrille Normandie-Niemen, a squadron of French pilots who left the comfort of England during the Second World War and went to Russia. Niemen is a town in Russia, and they fought with their comrades all through the Second World War. And this is commemorated in many places, but in particular there's one here in Paris that not so many people know, so I show you a picture of this famous building and this famous Place de l'Escadrille Normandie-Niemen here in Paris. So one should know more about these famous pilots. So that is why Vladimir Putin is in Normandy, to recall the valor of these Normandy pilots. Now, why they were from Normandy, I can't tell you. So I've exhausted my knowledge about this, but it's something we could look at in more detail. Okay, so there is some confusion about van der Waals interactions, and I want to differentiate between the physics and the math. So I'm going to talk about solutions of the Schrödinger equation. It could be that the physics is slightly different. Some physics books say that the way van der Waals interactions work is that molecules are very far apart, and then suddenly they spontaneously, at some distance, polarize each other. And a polarization looks like this. You have, let's say, a polar atom on the left, and on the right, you have a polarized atom. So this was neutral before. Here you have a dipole, and as they get closer, this becomes polarized. But that is an important interaction in chemistry for sure, but that is not how van der Waals interactions work. They're much more subtle. It looks more like this. So if you stand back, and I will take just two simple atoms, and I'll be talking just about hydrogen, so it's the simplest case possible. So if you look at a hydrogen atom, there's a nucleus and one electron running around, and it would look symmetric. The distribution of the electron is symmetric. And so these two would not seem to be different from what they would look like if they were completely separated. So from a certain point of view, there doesn't seem to be any obvious reason for them to be attracted, but they are attracted. Why are they attracted? Because what can happen is that the dipole that's formed by the nucleus and the proton and the electron is correlated to the position in the other atom, and that forms a dipole-dipole interaction. So this is a little bit strange, of course. This is the concept of entanglement. Do you really believe that physics works this way? We won't talk about that. I'm going to talk about the math now. I'm going to say, can you see this in the Schrödinger equation? So the Schrödinger equation allows you to have a representation of the electron distribution, and you can ask, is this an effect that one sees when you take two hydrogen, the model, the Schrödinger equation model for two hydrogen atoms and bring them from infinity? Do you see this sort of correlation, and does that account for the observed behavior of the energy? So here's what it looks like. You have the proton and an electron that are, one electron is near one proton, the other electron is near the other proton. I say this, that seems obvious, but in fact we'll see that we don't really control where these electrons are, and one could come over here if it wanted to. They can be, in fact, anywhere. The Schrödinger equation is an equation that models the distribution of the electrons, and it accounts for the possibility that they could be anywhere in space. Okay, we're going to think about a situation where the protons are separated by distance r, and then we have two electrons at some positions x and y. Each of those is a variable in R3, and they are totally unconstrained. They can be anywhere they want. And we'll write it in the positions x and y will be written in terms of the distance from, or the position with respect to one of the protons. Okay, now one of the complications of the Schrödinger equation is spin. And spin is a somewhat difficult concept to understand. I certainly have been very mystified about it until very recently. In fact, this example really helped me understand the way it works. So spin is a discrete variable. There are two states, up and down, for example. It's just z2 if you want. So they're just two discrete values. And then the wave function for the thing that describes the solution to the Schrödinger equation is this. Psi is related to the distribution of the electrons. Psi squared is something that can be thought of as the probability distribution of the electrons. And the ground state energy is given by solving an eigenvalue problem, and you look for the smallest eigenvalue. That's called the ground state. So if you look at just the single hydrogen atom, then this is very simple. And in a way, the single hydrogen atom is the only example you ever see in textbooks to try to explain the Schrödinger equation. And so it's very mystifying because you go from the simplest case, which doesn't have many of the important ingredients in it, to the general case very rapidly without seeing how various things like spin come into play. So in the case of the single hydrogen atom, this would just be a parameter, and there would just be two equations, and in principle, two lambdas. But the equations are identical because the spin is just an extra index. It doesn't affect the solution. Now, when you go to a more complex system, then it becomes more complicated. So let me just give you a little bit of the background on spin. So you can think of spin in two different ways. You can think of the wave function as depending on a spatial parameter and the spin parameter, or you could think of the wave function being just a function of space with a vector of values that are parameterized by spin. So these are two different ways of thinking about it, and it is useful to use both of them. And you can go back and forth with the mapping I call phi here. I'm being very formal, very Bourbaki style. But anyway, I find it very useful to think about this. I actually have never seen this written down before. I've never seen anybody write it in this way. People will go back and forth between these two representations without it being clear what they're doing. Now, it's very important to be able to multiply in the space of relevant functions. And since the right-hand side is some complicated vector space, you could imagine different kinds of multiplications, but it turns out it's just pointwise. So the relevant multiplication is just pointwise. So in each spin variable, you just multiply the two functions. For the single hydrogen atom, this doesn't have much importance, but when you get to more complicated systems, you do see some interesting effects from this because of what's called the Pauli exclusion principle. So the Pauli exclusion principle says that the wave function should satisfy the following relationship. And I've written it here just in the case of two electrons. And so in this case, we have a wave function of x1 and x2. These are three-dimensional vectors. position vectors in 3D, the positions of the individual electrons, and then the spin of the individual electrons. And it says the wave function has the property that if you permute the variables, keeping the spin together with the spatial variable, so I go from 1, 1, 1 to 2, 2 here in the first position, then you should get a negative sign. And this encapsulates, in a mathematical sense, the Pauli exclusion principle, which says that you can't have two electrons with the same spin state in the same system. So we'll just take this as our mathematical definition of the space of functions that we want to work with. And as I say, because of spin, it's a rather complicated space. For example, let's take an example. Let's suppose that we have a function f which is symmetric. I'll put the subscript s here to indicate that it's symmetric. And let me define psi in terms of this function by this pullback, this function that phi, capital Phi, that goes from one representation to the other. And over here, this is where I'm thinking about the spin being represented as something in a multidimensional space. Now that happens to be C4, because it's the number of spin variables here. So I can think of that as a matrix, a complex matrix. And I'll just take a symmetric function times this matrix, and I'll pull it back, and that will give me my wave function. And in particular, I'm going to take this matrix here, and I'm going to say that this is associated with, in the physics notation, this spin variable. So up, down, minus down, up, square root of 2 to normalize. And from a matrix point of view, it looks like this. The fact that these can be viewed as matrices is somewhat special to this two-electron problem. It would probably be better to just write this as a vector, but somehow intuitively it was more compact to write it as a matrix, and somehow I can somehow see it, the relationship. So there's no real importance that this is a matrix. It's just really a vector in C4. Okay, so there are other spin states that you can define in this way. So they're the up, up, down, down, and so forth. You can take linear combinations of them. And when you represent them as matrices, that allows you to define different size, different wave functions. And it turns out if these are anti-symmetric now, then this property holds when you take these spin variables. So what I've done is I've separated things in two cases. One case, I had this spin variable, and the appropriate function of space had to be symmetric in order to satisfy the Pauli exclusion principle. And for these three, it needs to be anti-symmetric. And of course, for more complicated systems, it gets more complicated. But here, it's relatively simple to think about. And if you go back to thinking about these as matrices, it's fairly simple to see that together with the one that I had originally, the one I called MS, which was just this simple one here. Where did it go? There it is. Here's MS. So if you take those four matrices, it's clear that you span all matrices. So you form a basis for C4, and so now I have a way to represent any function that satisfies the Pauli exclusion principle in terms of this simple representation. So this one involves a symmetric function, and these are all anti-symmetric functions of space. Okay, so what that means is I've said that this set of functions satisfying the Pauli exclusion principle is isomorphic to the set of square interval symmetric functions and three copies of the anti-symmetric square interval functions, if you will. This is all algebraic. The Sobolev space that we're using is irrelevant. We're just talking about the algebra here. Okay, so using that splitting, and you can take the Schrodinger operator, and it splits in this very simple way. So there's the operator acting on symmetric functions and three copies of the anti-symmetric functions. And so that means that we can split the eigenvalue problem in a corresponding way. So we have this as our eigenproblem. So this is the set of possible eigensolutions that we could have. So we could have a symmetric function satisfying this, or we could have an anti-symmetric function satisfying this. And of course, we could have the two eigenvalues be the same. We have to figure out whether or not our ground state is this one or this one. It's not at all clear. They're two separate problems. And so we have to think about that a little bit. Fortunately, in the case of hydrogen, it simplifies. The eigenvalue, of course, is a minimizer of the Ritz variational principle. The Rayleigh-Ritz, sorry, I should have said the Rayleigh quotient using the Rayleigh-Ritz principle. And so I can think of this now as I've got my space split in this way. And of course, the eigenvalue is minimizing over a certain subspace. And so that allows us to think about it as these two spaces are orthogonal, of course. And so we can reason about it. But what's interesting is that the minimum over the whole space, so unconstrained function, neither symmetric nor antisymmetric, but all functions, happens to be symmetric. So in this case, this algebraic aspect gets very simple. We can forget about symmetry, antisymmetry. We can just pose the problem on all of space. That's not going to happen in more complicated problems. But in this problem, it happens to work out that gives you a simplification of the total problem. So this means that the minimization of the Rayleigh quotient over all functions is the same as the minimization over symmetric functions, and of course, that means it has to be less than the antisymmetric one. So we have found the minimum. Okay, so this means in physics terms, the ground state is the singlet state, not the triplet state. So this was called a triplet state because there would be 3 copies of the one eigenvector. Okay, so now we get back to the PDE. So the Schrodinger equation is indeed a PDE, and there it is. So it's the Laplace plus a potential, which is somewhat singular. Here's the potential down here. And then I've written it in terms of what you would think of as the two potentials that would go with the two Laplace operators if there was no interaction. And then this is the interaction term. So it's these. So all this is saying, we go back here to our original picture, and we say, who's plus, who's minus. We just add up. It's just an electrostatic interaction, but we've got a Laplace equation thrown in to account for the quantum nature of things. Okay, so this is the problem we want to solve. We know we can, now we don't have to think about spin anymore for 2 hydrogens, and we can think about this posed for all functions. We don't have to worry about symmetry. Okay, so that simplifies things quite a bit. The singularities here are the real problem. And what's interesting is that it turns out this is really quite small where you think the electrons ought to be. It's quite small where the protons are. But nevertheless, it goes to infinity at some place. And so you have to account for the fact that, and for example, here you have a term that goes to infinity. You don't expect the 2 electrons to get close to each other. That just doesn't make sense. But they could. So you mathematically have to account for that. That's where the difficulty is in this. R is the separation distance. Yeah, R between the protons. R is this distance here. And we're going to let that be large and talk about what happens asymptotically as R gets large. When R is smaller, it's not right to think of this as van der Waals interactions. This becomes chemistry when R gets small enough. And I'll show you a picture, a graph that indicates that. Okay, so the ground state energy is the eigenvalue of this full problem. So the interaction energy is the difference between the eigenvalue that you get for a fixed R and what it would be at separated to infinity. The case when it's separated to infinity, it's known that the ground state for the 2 hydrogens would be -1, and so that's the expression we're interested in computing. And, right, okay, so that's the main point there. Okay, so here's the actual computed interaction energy for two hydrogens, not computed by us, but rather taken from two different sources. So one is a table that gives interaction energies, the blue pluses here, for various distances, r. So this is the r, the variable that I had before. And then here I've taken an asymptotic expression, which is of the form a constant times r to the minus 6. So we'll see that this r to the minus 6 is somehow the right asymptotic expression for the energy as you separate things arbitrarily far. And it just turns out that's as far as the table went. And so I drew the asymptotic line here just as a line. And you see that they are fitting pretty well, so that beyond here, if you drew the pluses, they would just sit pretty much on top of that line. And so it's also to say that the asymptotic expression is good to about 10 units, 10 units and larger. And these are the Bohr radii. So this is about 5 angstroms here. So it's saying that this asymptotic representation is pretty accurate for larger than 5 angstroms. 1 angstrom is about the radius of an atom, so it's not that far. And all of a sudden, this asymptotic expression seems to be very valuable. And this is what we would associate with the concept of the van der Waals interaction. Okay. Let me just make a couple of comments here. So this expression that we want to minimize, the Rayleigh quotient, the eigenvalue problem, is what typically has been used to compute these interaction energies. Just minimize this over something. And of course, it's the Ritz principle. So you can pick any functions you want and you'll get a number. Of course, if you pick more, you'll get smaller and smaller, but it may not matter to you. So this was originally done by London about 100 years ago, and he was able to show that the behavior was this r to the minus 6. He didn't get the constant right, but he could see that the behavior was r to the minus 6. Many people then worked on this for many years. Probably the most notable work was done by Lieb and Thierry, who showed rigorously that the r to the minus 6 is the correct expression for van der Waals interactions for any molecular systems. And again, they just simply picked a very clever test function in the Rayleigh quotient to do that. I'm going to be interested in a little bit more detail, and so I want to talk about the asymptotic limit. Well, that's what they were interested in as well, but so here's the equation, and now I'm going to introduce a small parameter. I'm going to say r cubed is epsilon, and I'm going to just start trying to understand what this is in some asymptotic limit. So the first thing to observe is that the potential itself can be written in terms of a very simple expression. This is just the dipole-dipole interaction for two dipoles separated by distance, two dipoles centered at R1 and R2. And so the potential turns out to be asymptotically, so that's r to the 3, r to the minus 3, excuse me, times this function plus something that goes to 0 at that rate. So this is just the asymptotic dipole-dipole interaction. So it says that in some sense in the limit, we just have to understand how two dipoles interact. Okay, so here is a description of how people would solve this problem. They start with the PDE, of course. They use the Rayleigh-Ritz method. They get some eigenvalues. And then they try to reason what happens as epsilon goes to 0, and in particular, try to get this C6 coefficient. And that's what has been done since London and Lieb and Thierry and so forth. And for some crazy reason, I wasn't happy with that. I wanted to see what does the function, what's the limit of the wave function look like. So the wave function had, the perturbation of the wave function is going to some limit, presumably, as r goes to infinity. And one would guess that that would solve some sort of limiting PDE, and then by taking a functional of that perturbation, maybe you get back C6. So that was the idea, to go this way rather than the the standard way like this. So this would be just the standard approach. So I say we're following Slater and Kirkwood, but Slater and Kirkwood made a simplification in this setting, but they weren't really interested in the wave function perturbation. They just wanted to get the eigenvalue. They used their insight to simplify the computation of the eigenvalue problem. But we're going to use this lower left side as the way to compute everything. So we'll use that to compute the perturbation in the eigenvector, the wave function, as well as the eigenvalue. Now, so we're just going to start with the standard perturbation approach. This turns out to be not very useful. It wouldn't really work theoretically. Or let me put it this way, I don't know how to do it, and I suspect it would be much harder if one were able to do it. But I'm just going to expand. I'm going to say that the wave function, which depends on this epsilon parameter, the distance r, is the wave function that you would obtain if you separated them infinitely far, plus epsilon times psi prime, plus epsilon squared psi double prime, and so forth. I just imagine I can have a Taylor expansion. And I do the same thing with the eigenvalues. And this is the equation that would be just the ground state equation for the two hydrogens separately. So the lambda naught is just the product of the two wave functions. And when you do the perturbation analysis, this is the equation you get. It's an eigenvalue problem. You have to reason a little bit about how do you perturb an eigenvalue problem. But this is what you get. The first order perturbation in the wave function satisfies an equation that looks like this. And it has to be orthogonal, of course, to the ground state what happens at epsilon 0, because we're perturbing off of an eigenvalue. The thing that's unfortunate about this approach is that lambda prime is 0. And this was noted originally by London, that it's a second order perturbation. And so it requires you to retain more terms in the expansion. And in fact, it formally would require you to prove that all of this made sense. And that would be rather hard to do. So it's fortunate we've been able to find a different path. But the perturbation is actually first order in the wave function. That is, the eigenvalue can be computed in terms of, don't worry about this function, this quantity for a second, in terms of epsilon squared times this expression. So it's the inner product of the perturbed wave function, which is not 0, and this operator B, multiplication operator, times the ground state for the fully separated hydrogens. So with that, the main thing to compute is this. It turns out this is exponentially small, and so the term that's left is this. And that's where you get the r to the sixth, the r to the minus sixth behavior, because epsilon squared is r to the minus sixth. And the real breakthrough here for us was that Slater and Kirkwood noticed that this splits. So this has a splitting in terms of this function B, the dipole-dipole interaction function, and a function that's only a function of the radial variables. So that makes it quite simple. So this would be a six-dimensional problem. This would be a six-dimensional problem, but it splits into a function that's a function of two variables and a function of four variables, but this one is an explicit quadratic expression. So when you work out when you stick that ansatz in and find out what equation is solved, you find that the two-dimensional problem looks like this. So it's not that we can solve this explicitly, but we have written it in terms of a two-dimensional problem, and it's a simple elliptic problem. So it's coercive, it's a very nice problem. The right-hand side looks like this, so it involves the wave function for the separated hydrogens. And the main result is that this expression is a solution to the original equation, and it's the unique solution in L2. Okay, so this is what it looks like. This is this psi prime. psi prime is a function of angular variables times this function t, and t only depends on two distance variables, the Euclidean norm of x1 and the Euclidean norm of x2. And here's what it looks like. So this is the asymptotic correlation. So this shows you how the electrons are correlated asymptotically as you go to infinity. And of course, the first question to ask is, does this represent correlation? So it's a little bit of statistics. You have to say, what does it mean to be uncorrelated? Well, if you have something, a function of two variables that's uncorrelated, then it has to be a product of those, it has to be a product of two functions of a single variable. And you can look at this and say, nope, that is not a product of two functions, because it would be, if it vanishes here, it's got to vanish everywhere. And I've blown up here the picture. So this goes from 0 to 10, and this goes from 0 to 3. And I've also divided by the radial variables, because this is the expression for psi prime. So psi prime is this expression times this function of angle only. And in fact, it also seems to satisfy Dirichlet boundary conditions at the case where one of the radial variables is 0. Okay, so I wanted to see this function for a very long time. I'm very pleased to see what it looks like. Of course, it seems to decay very rapidly. You can ask, how big is it? So here is the amplitude of that as a function of going diagonally across that two-dimensional region. Here's what the ground state wave function would look like, the thing that gets perturbed. And you see that the main perturbation occurs at about 1 Bohr radius. So that's half an angstrom, somewhere between half and 1 angstrom. When you do the numbers, this perturbation is not very large. It's actually a very small quantity, but it is what accounts for the van der Waals attraction. Okay, so now having this equation, having the wave function, I can then compute having the eigenvector, I can compute the eigenvalue. And here is what the calculations give. So I used Laguerre function approximation, just the standard Galerkin method for the 2D PDE using Laguerre functions. And I got the pictures you saw, and then doing the inner products as described gives you these coefficients C6. And I could go down to about a degree 15 Laguerre approximation. So that's a polynomial of degree 15 times e to the minus r. And then round-off error starts coming in. So it's, but it's, seems to give a consistent answer down to about that many digits. And it's more digits than are available in the most recent reference that took this, just the Rayleigh quotient approach. Okay, so very good. So now, all I need to do is convince you that that's correct. So I've showed you everything I have to say about this. That's the bottom line. The bottom line is that we know what the perturbation looks like, and it gives the right answer for the limiting coefficient that's been computed. So we have internal consistency that says that is the right thing. So I just have to tell you how I got that, or how I can justify it rigorously.
The van der Waals force in the books is it a constant over R6? That's all?
Yep, it's just a constant over R to the sixth. That is the right, yeah. And the constant has been, as I say, people have been approaching those digits, for years. And this latest reference that we refer to did also use the Slater-Kirkwood simplification, but all they use it for is to simplify the eigenvalue problem, simplify the Rayleigh representation of it. Okay, so how do we know we've got the right equation? We can't do that perturbation argument that we talked about. That would just be too complicated. We can't differentiate with respect to the small parameter and show that the Taylor expansion is, at least I don't want to try to do that. That would be very complicated to do. It turns out there is a completely different idea called the Feshbach-Schur method. So It uses the Schur decomposition. It was introduced into mathematical physics by Feshbach, and here's what it does. So what it does is it simply, rather than perturbing around a function in some sort of Taylor expansion, you simply project onto that function. So this only works in a Hilbert space context, but we're in a Hilbert space context, so we'll take advantage of that. So I simply project onto that. And so this is not, I'm not perturbing around psi naught, I'm projecting on it. So that means that my approximation is going to be a little bit different from psi naught. There'll be a constant times it. And if I could also project on a small subspace. It doesn't have to be a one-dimensional subspace. Same thing would work. And then what I have to do then is understand what happens to the other part, the orthogonal part. So here's the orthogonal part, y, I call it, yr. And so you can write an equation for psi r. This is just the Schur decomposition applied to this. So you get this expression for it, and you can begin to analyze it. And when you do, you get an equation for the error. So psi, yr is going to psi prime in this way. So it's going to 0 at rate r to the minus 3. So when you multiply by r to the 3 and take the difference, you get an error term. And the error term can be bounded in terms of the differential equation and a bunch of things on the right-hand side. And so you have to analyze each one of them in turn. This is saying that the potential is approximated by this dipole function. This is this term that I said is exponentially small, and here is the error in the, or the, not the error, but the difference in the eigenvalues multiplying psi prime. And then here is a term that is the potential applied to psi prime. This one is the most troublesome term. And in full disclosure, I have to say we have not found the optimal way to handle this term yet. But I will explain what the complications are for this term and some other things just so you get a sense of where the complications are. So as I say, the magic is to project onto psi naught instead of expanding around it. In addition, the Feshbach-Schur perturbation suggests some numerical schemes, and that, I think, is, for me, the best news here. I sort of resisted deriving this proof of the correctness of this equation for a long time, and then when I went through this argument, this argument was developed recently in a thesis, and we're using that thesis very heavily. I'll give the references at the end. So in doing that, I realized, well, wait a minute, this Feshbach-Schur perturbation actually leads to a numerical algorithm, or something that can be turned into a numerical algorithm, where you have here just the Schrodinger operator with, say, the separated ground state operator for the two hydrogens. That times the perturbation term is given by things you can compute iteratively. So I think that's very nice. So that's ongoing work to understand how that would be useful. And what's interesting is that it doesn't require, this is not the asymptotic limit as r goes to infinity. This can be done for finite r. Okay, but now I said I would tell you a little bit about these terms. So you have to show that the potential is small when the error in the potential is small when applied to the ground state wave function. Okay, so it's fairly simple. You look near the origin, so I'll let k be a parameter here, and this is small by construction, and so this has to be bounded, but one can do it. So near the origin, you have an estimate that says it looks like r to the minus 3, and if you put in how k impacts it, it's r to the minus 4k cubed. Okay, so that gives you a bound on this for this expression. This expression can be bounded in a fairly straightforward way because the wave function is going down exponentially, and this is just a simple quadratic. It leaves one more term to do, and unfortunately, that's a little bit complicated. So what you need to do is you need to break up this potential into 3 parts and analyze each one separately. So you have to localize around where that individual term is large, and you can. Once you do that, you get the right answer. You take k equal to log r, and you get the stated result. So here is that estimate around the singularity. I'll just, in the interest of time, I'll skip over that. Okay, but so that shows that the perturbation in the potential is small. That was a key thing. But I also need to know that this Schrodinger operator is invertible. Here, this perp means that it's perpendicular to the ground state size 0. So one can do this. Let me just sketch the difficulties here. What you need to understand is that it's possible for the electrons to go over to one proton, and that would be an ion. So you need to understand what's the ground state energy of a hydrogen ion. And that's known, it turns out, and it's higher than the 2 hydrogen ground state. So that's a critical thing, and that allows us to prove this lower bound for the operator. So here's the operator again, and the point is that there are some. We're trying to show that this is bounded below. There's some negative terms that cause us difficulty. These singularities are very far away. So the protons are at 0 in each of the 2 variables, and this is very, very far away. But we have to control them. And so here's the way to think about it. I'm in this situation where I have, in these variables, the proton is here in the middle of the box. The electrons, we assume, are around here. But these potentials are infinite in this hashed area. Okay. And I could as well have a different way of thinking about it. So this is the full potential. So there's 6 terms. And I've assumed here that one electron is near the ith electron is near the ith proton. This is the position of the ith proton, the r times e. And that's the rest of the terms. But as well, we could have both electrons near one proton. That would be the ionic case. And so we have to somehow convince ourselves that that doesn't cause problems. So that would be the situation here. If both electrons are here near one of the protons, then the singularities on the interaction potentials appear here. And there are 2 other cases that you have to think about, which correspond to the other ion. So this would be the other ion. And then this is just kind of crazy, but you have to consider that you might have gotten it wrong, that the ith electron might be near the jth proton. So you have to consider all 4 of those cases. And the way it's done is very clever. It's done using a partition of unity. That's done where the partition function is the square of something. And what you can do is you can choose the partition of unity to separate these 4 different potentials so that the particular partition function times the particular potential is bounded below by something manageable. So there are 2 ionic cases and 2 non-ionic cases. There's a thing called IMS localization, which is really just the observation that if you write the partition of unity this way, and I think of, well, let me start over here. So suppose I wrote down this expression and I differentiated j. If I take the operator onto j, I'll get something. It turns out it's that. So then the result will be this. So this is that formula. It's not very complicated. But it's just what you need to give bounds, lower bounds, on these expressions. Okay, so the ionic case and the regular case are a little bit different, and there's a lot of considering of commutators. So we have to commute this projection with the multiplication by ji. These sorts of bounds are the things you have to consider. So, each one of these represents about a page of calculations, but nothing profound is going on. So this completes the proof that that representation I gave before is correct. Okay, so where do we go from here with this? Well, as I say, maybe the most interesting thing is that this Feshbach-Schur algorithm gives you a way to think about solving electronic structure iteratively, and where you have a simple a fixed ground state operator that you work with in each iteration. So you can do all kinds of things whatever, if you need a preconditioner, or you could factor it, or whatever you do when you've got a fixed differential operator and are solving iteratively, all those techniques can be brought to bear. And I claim this could fill a gap between the asymptotic range, which we have figured out what that is, and the standard conventional electronic structure methods, which are very good at analyzing what happens when atoms are very close together. But there's a middle range where they would actually break down because they use Gaussian functions that die too fast. And so they don't do very well when, say, things are separated 4 or 5 angstroms apart. So you might say, well, there's no interaction there. But no, in fact, when you go back and you look at this, the actual interaction energy, which is, did I go over it? I must have gone over it. No, maybe it's back here. Sorry. Should have another copy floating around. I think I'll put one in there. So this is the asymptotic range. This is the part that you would get right with Gaussian and codes like that. But in here, something interesting happens, and I find it very interesting that this energy seems to go up. I would have thought it would go down from the asymptotic range, but it goes up. And I showed this to Eric Cancez, and he said, that's chemistry. So now I understand what chemistry is. It's this interaction at a distance, which is very complicated. It's hard to describe. There's no asymptotic description of it. Okay, but I think this Schur method could be very effective in this range because the perturbation term, the R, is fairly large, and so you can hope that you would get good convergence in just this range. Probably wouldn't work very well here, but this is the domain of standard software. Okay, so what else? So I think this could be used. We don't have the simple splitting that occurs for this with 2 hydrogens, but we could use the technology to solve for 3 hydrogens, and there's a lot of interest at this point in the 3-body interaction, just understanding just how big it is. Asymptotically, as you separate the hydrogens to infinity, the van der Waals interaction would be the sum of the 2-body interactions, but when you're not so far away, it's interesting to know how big is that 3-body interaction because, for example, most molecular dynamics codes are based on just 2-body interactions. And I think this will also allow us to solve other 2-electron and 3-electron systems and be able to exhibit the electron distribution, which for me is something that I would like to see. So to get the wave function, not just the eigenvalue. Okay, so let me just give my credits here. So most of the collaboration was with Eric Cancez, most of the ideas about electronic structure calculations. Of course, I'm a novice in this area. He's an expert. We had a very nice collaboration to work all this out. I have a postdoc at University of Chicago who's been starting to work on this application of the Feshbach-Schur algorithm. And let me acknowledge the National Science Foundation that provided some funds for this. And I'll take questions.